To understand how public discourse takes shape on social media, we have to look past individual opinions and map the underlying structures that dictate how information is consumed. These structures are built on tropes, recognizable devices used in narratives to convey specific themes. Online content producers rely on them constantly, exploiting our familiarity with preconceived concepts to package complex arguments into easily digestible formats. In academic research, these devices are categorized into distinct narratives. You might recognize appeals like Defend the Weak, which positions the speaker as a protector of vulnerable populations, or Time Proves Me Right, which claims a sense of inevitable validation. When analyzing discussions around vaccine hesitancy, specific patterns emerge repeatedly. The natural is better trope, for example, is consistently deployed to promote traditional or organic solutions over modern medical innovation. In other cases, the scapegoat trope is utilized to streamline complex systemic problems by assigning direct responsibility to specific high-profile individuals or organizations. Identifying these patterns is a distinct challenge from standard algorithmic fact-checking, which evaluates the factual accuracy of a specific claim. It is also separate from propaganda identification, which flags malicious intent and coordinated manipulation, and it differs from conspiracy theory flagging, which tracks the spread of specific false narratives. Tropes operate on a different layer entirely. They are the structural mechanism of a narrative, existing completely independently of the text's actual substance or veracity. The core technical challenge in studying these devices is extraction. We need to identify multi-label, highly context-dependent, abstract patterns from a massive volume of noisy 280-character text segments. Mathematically mapping this hidden infrastructure is the necessary prerequisite to fully understanding how modern algorithmic public discourse functions. The standard industry assumption is that massive large language models like GPT 3.5 or Llama 3 should easily identify this kind of human narrative nuance. To test this, researchers applied zero-shot prompting to these models, asking them to read a social media dataset and categorize the tropes without prior domain-specific training. This chart shows initial results. Zero-shot prompting massive LLMs yields surprisingly poor F1 scores compared to a specialized architecture. Expanding to a scatter plot shows a precision versus recall deficit. General models struggle, generating high volumes of false positives by predicting absent tropes. These models fail to capture the implicit, highly contextual linguistic cues that humans use to communicate complex ideas within a brief 280-character limit. This failure is compounded by the inherent sensitivity of general LLMs to slight prompt variations and hyperparameters like temperature settings, which cause inconsistent outputs. Sheer parameter size cannot substitute for domain-specific fine-tuning when the objective requires capturing precise semantic nuance. The solution requires building a specialized multi-label classification pipeline from the ground up. Researchers constructed a raw dataset of 3,300 social media posts to train and validate this model. The training data maintains a strict domain split. 63% of the text focuses on vaccines, while 37% covers immigration. To establish a reliable ground truth, human annotators executed a rigorous 4-phase qualitative coding process. This flowchart illustrates the workflow, beginning with Phase 1, familiarization, where researchers reviewed thousands of topic-related posts to understand the overall narrative landscape. Moving into Phases 2 and 3, the process transitioned from open coding to framework development, systematically organizing the raw text into 9 distinct trope themes. Finally, Phase 4 involved verification, requiring annotators to reach a unanimous agreement on the final 3,300 annotated posts. This precise dataset enabled the training of the winning architectural asset, COVID-BERT-FT, a pre-trained transformer model. At 336 million parameters, it is vastly more efficient than the multi-billion parameter architectures of prior LLMs. The specific training technique involves applying a cross-entropy loss function directly to the classification layer. By weighting this loss with the inverse frequency of the class samples, the model neutralizes the negative impact of imbalanced training data. This allows it to accurately identify tropes like skepticism towards authority, regardless of how often they appear in the data. As a result, COVID-BERT-FT achieves a weighted average F1 score of 0.65, drastically outperforming the general LLMs. A targeted architecture paired with weighted loss functions allows smaller models to map abstract narrative structures that generalized AI simply cannot see. Performance naturally varies across the 9 trope categories, with the model showing a particularly high success rate for classes like too fast. The linguistic cause for this success is clear. These texts rely heavily on easily identifiable bigrams. Encountering paired trigger words like clinical trials or experimental vaccine, the model's classification is highly accurate. Contrast this with the noticeably low performance on the time proves me right trope. The mathematical reason for this deficit comes down to ambiguous n-grams and a critical lack of training samples representing that specific class. This limited data also introduces the risk of overfitting on certain keywords, which directly leads to false positives in some categories. However, the data reveals a far more critical finding. The narrative mechanics learned in the context of vaccines apply successfully to the context of immigration. This chart shows the Pearson correlation heat map matrix for the full dataset, visualizing the structural relationships between all 9 tropes. Notice the lack of strong negative correlations across the grid, suggesting that tropes operate as independent devices that easily coexist within the same text. This correlation matrix is isolated strictly to the vaccine subset, giving us a granular view of topic-specific behaviors. When the data is restricted to a single domain, specific variances and new correlations emerge, particularly around the interactions with the wicked fairness category. Because models trained on combined data consistently outperform subset-specific ones, we can prove that tropes function as domain-agnostic mathematical structures. This raises a practical question. Are tropes just another name for propaganda or conspiracy theories? The research defines 3 distinct spheres of misinformation analysis: tropes, persuasion techniques, and conspiracy theories. This diagram visualizes the statistical overlap between these dimensions, proving they track entirely different linguistic behaviors. Tropes and conspiracies overlap just 24% of the time, confirming the model isolates narrative mechanisms from specific arguments. The data shows an even smaller overlap with persuasion techniques. Unlike propaganda, which is inherently designed to manipulate, tropes can be deployed neutrally or even constructively. For instance, a hidden motive trope doesn't just spread doubt. It can be used to legitimately hold authorities accountable for policy failures. Tropes represent a distinct, quantifiable dimension of text analysis that is completely orthogonal to traditional misinformation flagging. Researchers tested the model's ultimate validity by applying it to entirely out-of-distribution data, like internet memes. Transferring a model trained on structured tweets to the noisy, low-context syntax of memes is historically difficult. By prioritizing precision over recall and applying a high-confidence threshold to filter for only the most certain hits, the model achieves a binary F1 score of 0.943 on this unseen data. Concepts like defend the weak and hidden motives prove to be the tropes that transfer most successfully into these external formats. Mapping this information moat is essential for promoting evidence-based communication and actively monitoring public discourse. Identifying the Internet's narrative infrastructure requires specialized, tightly focused machine learning architectures, rather than relying on generalized, massive parameter models. Mathematically defining these textual structures is the prerequisite to understanding how algorithmic public discourse and modern social behavior are truly built.